Okay, so this is the second part of our discussion on steady state error. We defined the steady state error in the first lecture, and we checked and we discussed the final value theorem, which holds when the system is stable, and we realized that pure integrators play an important role in the steady state error. Now let's define these static error constants. Position constant Kp is defined as the limit s going to 0 of L of s. What was L of s? L of s was the loop gain transfer function. Or sometimes called loop gain function. So if we set s to 0 and calculate the limit of L of s, whatever we end up with will be called position error, or I'm sorry, position constant. And we know that it can be seen through the final value theorem that the steady state error for the case of unit step will be 1 over 1 plus Kp. So whatever this Kp is, if we put it in this equation, the steady state error for unit step will be calculated. The next constant is velocity constant. We multiply L of s by s, and we then set s go to 0. Whatever we end up with will be called velocity constant. And through final value theorem, it can be seen that the steady state error for the input of ramp will be 1 over kv. So whatever kv is, 1 over that will be the steady state error for the ramp case. The third static error constant is acceleration constant. We multiply the loop gain transfer function by s square, and we then let s go to 0. Whatever we end up with will be acceleration constant. And the steady state error for the case of parabola input will be simply 1 over Ka. So these three constants could either be 0, a constant number, or infinity. For example, if Ka is infinity, then 1 over Ka will be 0. So we know that the error for the parabola input of such a system will be 0, the steady state error. So these constants could be 0, could be a constant number like 5, or could be infinity. Now let's talk about system type. The system type is defined as the number of pure integrators in the loop gain function. So if we write the loop gain function in this form, this number will be the system type, the number of pure s's in the denominator of the loop gain function. So see, this is not a pure s. This leads to a pole, a 0 at minus z2. Or this guy leads to a pole at minus p1. But this guy leads to a pole at 0, at origin. These are called pure integrator, as we discussed in the first part of this lecture. So the number of repeated poles at the origin is the system type. But we can represent this L in another form as well. We can multiply these terms, this, and we can end up with a polynomial in the numerator and a polynomial in the denominator. And we can factor this S out from the denominator. Then we end up with such a thing. See, a polynomial in here, where S to the power of n is factored out. A polynomial in here, where k is factored out such that the constant term in the parentheses in the numerator and the denominator are 1. If you make these guys 1, then whatever you end up with in here, this k, will be the static error constant of the system. And of course, this n will be the system type. So note that for this k in here, in the star equation to be the static error constant, the constant terms in the parentheses have to be 1. So we make them 1. Whatever we end up with in here, whatever number we end up with, will be k. And which k? We have 3 static error constants: position, velocity, and acceleration. Which one of these k's is this k? The answer is, if the system type is 0, the resulting k will be the position error constant. If the system type is 1, the resulting k will be the velocity error constant. If n is equal to 2, the resulting k will be the acceleration error constant. And these can be confirmed using these relations which we have for Ka, Kv, Kp, Kv, and Ka. For example, if we set S go to 0, then S go to 0 will make this whole parenthesis in here 1, because the non-constant terms will become 0 and 1 will remain. All these will cancel and 1 will remain. If n is equal to 0, so this guy does not exist in here, whatever we end up with is just this k. We end up only with this k. So that Kp, this guy, will be the same as this k, providing n is equal to 0. So these two also can easily be checked using their formula. So this example, find the system type and the static error constants for this system. What we do, we calculate the loop gain function, the multiplication of the transfer functions around the loop. So 2 times this thing is the loop gain function. So let's multiply this thing by that. We end up with this in here. As you see, we cannot claim that this is the k, the static error constant, because we do not have 1 in here and in here and in here. So let's factor 4 out to end up with 1 in here, and also factor 2 out to end up with 1 in here. Now this 8/2 is the static error constant. What's the system type? It's equal to 0, because we do not have an s to the power of n in here. We do not have this guy in the denominator. So the system type is 0. When the system type is 0, this k will be the position constant error. Position constant. I'm sorry, not position constant error. Position constant. So, what about kV and Ka? We can use the formula. kV is S multiplied by L of S. Its limit when S goes to 0. So if we multiply this thing by S and we calculate the limit as S goes to 0, we end up with kV equal to 0. Ka is also 0, because if we multiply this thing by S squared and we calculate the limit S going to 0 of this whole thing, we'll end up with Ka equals 0. Because these S going to 0, this thing will result in a constant number. When that number is multiplied by S squared and S goes to 0, the whole thing becomes 0. So we found the static error constants and the system type. Now, here's a table, a nice table for assisted error, which relates the system type, the steady state error, the input, and the static error constants. This is given for 3 different basic inputs: step input, ramp input, and parabola. For system type 0, system type 1, and system type 2. It says that if the system type is 0, then when you apply this step input, first of all, the Kp, the position constant, will be a constant number. And when you apply the step input, the steady state error will be 1 over 1 plus Kp. If the system type is 0, the velocity constant will be 0, and if you apply ramp input, the steady state error will blow up. The parabola input, system type 0, which means no pure integrator, a steady state error will be infinity, and the acceleration constant will be 0. System type 1, unit step, will result in a steady state error equal to 0 and the position constant of infinity. Ramp input, velocity constant being a constant number, the steady state error 1 over kV. Parabola input, for system type of 1, acceleration constant 0, steady state error infinity. Same thing in here. As you see in here, if the system type is 2 and the input is parabola, then we end up with a steady state error of 1 over Ka. The steady state error for such a system, if the input is ramp, will be 0. The steady state error for such a system is the input, if the input is step, will 0. And we know that because it has 2 pure integrators. And we know that steady state error for unit step is 0 when we have at least 1 pure integrator. For ramp, it is 0 if we have at least 2 pure integrators, and we do. But this is calculated using final value theorem, as we'll see in the next example. So we'll refer to this table as the steady state error table. And it's given as table 7.2 in the text. So let's proceed to an example. Design a controller K, a constant number K in here, such that the steady state error is less than 0.2 for the unit step input to the system. So this guy being 1 over S, the steady state error, this error in here, we want this error to the final value of this thing, I mean as time goes to infinity, be less than 0.2. This is a system, this is a plant, a given bicycle, a ship, an airplane, a car, and we're going to design a controller, this K, such that the steady state error, the final value of this guy, this error, is less than 0.2. The solution: initially check for stability. Note that the final value theorem does not hold for unstable systems. So let's find the transfer function, closed loop transfer function. The transfer function relating the output of the whole system versus its input. C over R. Is the transfer function in the direct line over 1 plus the loop gain function. When we simplify it, we end up with this transfer function. If we do Roth table for checking the stability, we'll see that this parenthesis and this one have to be positive in order for the poles to be in the left half plane, to be stable, for the system to be stable. So by Roth table, the system is stable if we have this condition and that condition. And it's not hard to see if K is greater than minus 1 over 2. Both these two conditions are satisfied. So for stability, we need K greater than minus 1 over 2. Now we proceed to final value theorem, FVT, final value theorem, which says that ESS equals the limit of S going to 0, S multiplied by E of S. But E of S was this transfer function, E of S, over R of S. So we find the transfer function, which is 1 over 1 plus L of S. We multiply it by the input. So this is the input. And we multiply the whole thing. So this whole thing will be E of S. Then we multiply the whole thing by S and we let S go to 0. This L will cancel this L. I'm sorry, this S will cancel this S. And then we'll end up with 1 over 1 plus limit of L of S. S going to 0. Let's replace L of S with its actual value, which we found for this example to be this thing. And if you set S go to 0, it will be equal to this, which is equal to this. So if you want the steady state error to be less than 0.2, the Laplace inverse of this thing, which is itself, has to be less than 0.2. Therefore, 1 plus 2k has to be, this has to be 5. 1 plus 2k has to be greater than or equal to 5. The reverse of this inequality. The inverse of 0.2 is 5. So the inverse of the whole thing will be this. So k has to be greater than 2 for the steady state error to be less than 0.2. But Does this K lead to the stability as well? Yes, because K greater than or equal to 2 will be greater than minus 1 over 2 as well. So for steady-state error, K equals to 2 or greater than 2 suffices. It will lead to the stability and will lead to the desired result. If such a K is not stable, this will not be resulted, because this was calculated through final value theorem, which holds if the system is not unstable. For stable systems, we do the whole thing. So such a K results in stability. Now we proceed to the rest of the steps to satisfy this condition. Whatever K we end up with, we need to check if that is stable as well or not. And here it is. So we're good. Any K greater than 2 will be the answer to this example. Any K greater than 2. So equal to or greater than 2 is the answer. There's a shortcut solution also using the steady-state error table. We need to find the system type and the static error constants. We rewrite the loop gain function in this form, and then we factor these 2 and 4s out to end up with 1 in here and 1 in here. We end up with such a thing. Do we have s to the power of n in the denominator or not? We do not. So the system type is 0. Whatever constant we end up with in here is a static error constant. But because the system type is 0, this constant will be the position constant. And by the table, we know that, see, from the table for system type of 0 and step input, we know steady state error will be 1 over 1 plus kp. So in this example we have kp, so by the table steady state error is 1 over 1 plus kp. Let's replace kp with a relation, simplify it, we end up with the steady state error equals 1 over 1 plus 2k. And for this thing to be less than 0.2, we need that. So in this shortcut method, the final value theorem was not explicitly used, but the table which we used, the steady state error table, was based on final value theorem. So we still need to make sure that the resulting k will lead to the stable system as well. So that Roth table part, which we did in here, is still required, but we do not need to go through the final value theorem. So there are two ways: one, final value theorem; the other one, the steady state error table, and they will give the same result. Now let's discuss a few questions. Question 1: what is the steady state error of this system if the input is not unit step? It's actually ramp. Based on the steady state error table, we have the steady state error equals infinity, regardless of the selected k. Because in the steady state error table, we have for the system type of 0, ramp input results in a steady state error of infinity. Can we select a K which can change the system type? No. See, in here, whatever K you pick will not change this system type. Or in here, the loop gain function, see in here, the loop gain function, whatever K you pick, it will not create a pole at the origin, because K is supposed to be constant, a number. So it cannot change the system type, and when we have the system type of 0, the ramp input will result in a steady state error of infinity. Question 2. Can one design a suitable K such that a steady state error is 0, exactly 0, for unit step in the system? No. Since LFS does not have any pure integrator, the unit step steady state error will not become 0. But it can be made constant, like we did. Like, let's say, for example, steady state error be less than 0.2. But we cannot make it exactly 0 for any selected finite K. If you want the steady state error to be exactly 0, look at this table. The steady state error is 0 if you can change the system type to type 1. See? Then the steady state error is 0. Or to system types of higher than 1. Steady state error will be 0 for the unit step. So let's proceed to the third question. What K leads to the same interval for the steady state error for the input of 5 times U of t? Note that a steady state error table is given for simple inputs, including unit step. In here, the input is 5 times unit step. But due to the linearity of the system, whatever the steady state error is for U of t, the steady state error for 5 times U of t will be 5 times more. Will be 5 times that. 5 times this thing. The steady state error for U of t. So, if we find the steady state error for U of t, we multiply it by 5, the result will be a steady state error for 5 times U of t. Another option is using final value theorem, as done initially in this example. Let's use this thing, final value theorem. A steady state error, S goes to 0, S multiplied by E of S. In E of S, this is the transfer function of E of S over R of S. So let's multiply it by the input. You see this 5 in here? That's because the input is 5 times U of t. If we do this and we simplify it, we'll end up with this thing. A steady state error is 5 over 1 plus 2k. When the input was unit, we had 1 in here. Now we have 5 in there. So in order for the steady state error to be less than 0.2, we need 5 over 1 plus 2k to be less than that thing. So we need this, the inverse of this inequality, and when we simplify it, we need k to be greater than 12 for the steady state error. of the input of 5 times u of t to be less than 0.2. And note that this, we still need to check to make sure that this will result in a stable system as well. And it does. Because any k greater than minus 1 over 2, see, based on this table, k, I'm sorry, Roth table, any k greater than minus 1 over 2 will be stable. So k greater than or equal to 12 will also be stable. So we need to make sure that the resulting k through this final value theorem will satisfy the condition of stability of the overall system as well. Okay, that's it, our discussion for the second part of the steady state error. Thank you guys.